Today, I would like to present my final report. The title is Comparison PID Control and Linear Model Predictive Control to DC Motor System. So this is my research motivation. Due to the excellent speed control characteristic of the DC motor, it has been widely used in industrial, such as cars, trucks, and aircraft. Even though it's the maintenance of the system, maintenance of the DC motor are higher than the induction of the motor. To achieve effective performance in matching the output speed, the proportional integral control is commonly used for DC motor speed control, but most of people use the method of the trial and error to find optimal PID constant, which certainly requires a lot of time. MPC is the technique to control the linear or and non-linear system, and the response will be get the zero state error and the low transient response, and it will decrease or remove off peak overshoot. The performance of the linear MPC in this report will be compared with the PID controller, which is the traditional controller used to use in industrial for DC motor system. So this is the my problem formulation. We have two sections in here. In the left side is the electrical circuits, which is L. L is inductance and R is a resistance. So from the Kirchhoff voltage, we obtain the equation 1, which is Vs equal Re plus L di over dt plus E. So from this equation, we can find E. E is the back EMF, and we get the equation 2, E equals minus Re minus L di dt plus Vs. So for the right side, this is the electrical mechanical system of the DC motor. So based on Newton's second law of the motion, we can find the torque of the DC motor. Te is equal Kf omega m, which is omega m is a angular velocity of the motor DC, plus G is a rotor inertia, d omega m over dt plus TL. TL is the mechanical load. So for the assumption, TL equal to 0 because we have no load in the DC motor system. So after we found the equation 2 and equation 3, we have to convert to Laplace transform to get the transfer function. So for the electrical equation number 2, we found this equation before, and we know back EMF equals to Ka and omega m, so we can find the this equation. From this equation, we transform to be Laplace transform, and we get equation 4 SA equals minus A R over L minus Ka per over L omega m plus 1 over L Vs. From the mechanical equation 3, we found this before, and we know Ta is equals Kt omega m. So for this equation, we can derive to be this equation. We move the Kf and omega m to the left side, and we over the left side to G, and we found this equation, and we converting this equation to Laplace transform. So the last, we found the Laplace transform of the mechanical system, which is the S omega m equals E Kt over G minus Kf over G omega m plus 1 over GTL. So that I ever told before, TL equals to 0 because we have no load on the mid motor DC motor. So from the mechanical equation, we can canceling this equation, and we can write again, and we found this equation. So from this equation we can found the E, and we found E equals to S omega m plus Kf over G omega m per Kt over G. So E will be substituted in the electrical equation, and then we get this equation, and we derive the equation, and the last we found the equation 6. Vs equals to this equation multiplied by omega m. So for transfer function, we know that the general equation of the transfer function is a output divided by input. So for this report, I use omega m, angular velocity of the DC motor, to be output, and source voltage to be input. So from the equation number 6, we can found the transfer function of the motor DC, and the last we assumption the friction constant is small, so Kf is 0. So the last of the transfer function of the DC motor, we get this one, omega m over Vs equals to Kt over S squared GL plus G S squared multiplied by G and L, with G is a rotor inertia and L is a inductance, and plus resistance multiplied by rotor inertia multiplied by S plus Ka and Kt. Because of Ka and Kt is similar, so we can derive K multiplied by K, or K square. So after we get the transfer function of the DC motor, we can found the controller. We can design the controller, which is the PID controller and the MPC controller. So for the characteristic of the PID controller, we know that Kp and Ke will be decreased the rise time, and Kd will be the small change of the rest time, and Kp have increased the Kp and Ke increase the overshoot of the system, and Kd is a decrease the overshoot, and Kp have the small change of the settling time. Ki increase the settling time, Kd is a decrease the settling time, and for the steady state error, Kp will be decreased the steady state error, Ke will be eliminated, and Kd will be have the small change of the steady state error. So how to find the PID parameter? For this report, I would like to use the Ziegler-Nichols, the first method, to find the parameter of the PID controller. So after we get the closed open loop of the system, we can draw the tangent line at the inflection point, so we can find the K, L, and T. From this parameter, we can find the parameter PID, which is P. To find Kp, we can T over L. We can find by T over L. And Kp for Pi, we can find 0.9 T over L and L over 0.3. And PID 1.2 T over L will be NTI 2 multiplied by L. So for the model predictive control, MPC is the one of advanced control. The MPC works from the past data, and they estimate from the past data to future data. And this is the line of the current time, and MPC will be predict from the past step to the future step by step. And this is the MPC structure, and we have a model of the system. The transfer function of the system will be input, the reference point, and the MPC will be predicted the output, and the feedback of the system will be in the optimizer. The optimizer, I use the cost function, which is the G equals to RS. RS is the matrix of the one multiplied by NP minus Y. Y is the output transpose, and multiplied by RS minus Y plus delta U. Delta U is the metric of the prediction input, multiply delta U transpose and multiply by R head. R is the weight of the control input, and multiplied by delta U. So for the optimizer will be calculate the cost function. So after they calculate will be to be the future inputs of the model system. So for this report, I would like to design the methodology of this report. The first time I did is find the transfer function of the DC motor, and after that simulate the transfer function to obtain the open loop of the system. After that, I have to find the parameter of the PID using the Ziegler-Nichols tuning, and I compare the PI, and PID controller to find the best controller. After that, I designed the MPC controller with the vary of the MPC and NC using MATLAB, and simulate MPC and choose the best controller. And the last, I compare the best controller of the PID with the MPC with the vary of the NPC and NC. So this is the numerical example. In the left side is a motor that I use for this report, Maxon DC motor F2140. And this is the datasheet of the Maxon DC motor. So from the datasheet, I substitute to the transfer function of the DC motor, and I get the transfer function of the DC motor. After that, I would like to simulate in the MATLAB, and I get this response. From this response, I draw the tangent length of the system based on the Ziegler-Nichols first method. So I get the K equals to 18016, and T equals to 0.36, and L is equals to 0.025. So after I get this parameter, I can find the parameter PID that I can submit in the PID controller. So this is the table of the parameter, the PID. So this is the control of the simulation of the PI and PID controller. So we can know that this is the response of the system when I use the PI and PID controller. The green line is the step function, the step response, and the blue line is the PID controller have the higher overshoot than two controller, and the red line is a PID controller. This is the best controller that I choose, and the yellow is a P controller. P controller cannot reach the set point, so I didn't use this controller. So I decide to use PID controller to be to compare with the MPC. And this is the design of the MPC controller. For this report, I compare with the bit varying NP. NP is the prediction prediction horizon, and NC is a control horizon. So for in the left side is a input of the simulation MPC in MATLAB. So for the right side is the output of the simulation of the MPC in the MATLAB. So after I compare NP equals 5 and NC equals smaller than 5, which is NC is a 1, 2, 3, 4 until 5, I get MPC with the prediction horizon equals to 5, and the control is equal to is better performance. So I do it again with the varying NP, with the NP is equal to 10 and with NC equals to smaller than 10. So I get MPC with NP equals to 10 and NC equals to 2. And I compare again with the NP5 and NP10, and I get NP10 and NC2 is better performance. NP10 is the red line, as and the blue line is NP5. And after that, I doing simulation and compare again with the PID controller. And for the PID controller, I get this response in the blue line, and the red line is the step response, and MPC controller is in the yellow. So the from this response, I calculate the rise time, transition time, and settling time, and overshoot. And MPC have the 0 overshoot, but PID have the still have the smaller overshoot, 0.57, and settling time of the MPC is 1, and PID have 0.0154, and rise time PID have the 3.04 E multiplied by 10 minus 5, and MPC have a minus 9.36 multiplied by 10 times minus 7. So from the conclusion is a comparison between PI and PID controller with Ziegler-Nichols deliver that PID have the better performance than P and PI. With the parameter of the PID is equal to 17.15, Ka equals to 335.08, and Kd 0.21. And comparison between MPC with varying NP. So I get the MPC with the NP10 and NC2 is the better performance than other MPC, and I compare again between PID and MPC. The result is MPC can success to reach the reference than PID. PID controller still have 0.5 overshoot, whereas MPC didn't have overshoot. However, PID have more quickly to reach the reference, specifically with settling time at 0.0154. So this is the final report that I can tell. The last I say thank you.